So in other videos that you've seen that I've done, or maybe Raj's videos that you may have seen, we've talked about how our architecture is kind of designed for multi-gigabit, 10 gig, 20 gig and higher deduplication as well as just general man acceleration. So I want to take a few minutes and talk about how we're different and what we've studied in the other architectures out there, the ones that the WAN optimization vendors use, and what we really found in many respects disconcerting as to how, what's going on there. So of course, as being a startup, when we started, we spent a lot of time looking at the competition. So we spent a lot of time looking at, well, how do they do things at the hardware level, right? I mean, what is it that they do inside the box? And I want to kind of give you at least our analysis of what's going on. And of course, if you guys have any questions, concerns, comments, please, feel free to find me on Twitter or email me. You can find my email on the YouTube website. But let me kind of start talking about what the WAN optimization vendors do in terms of just a black box, kind of high level, what's going on in that system. So if I were to kind of draw, this is a very bad representation of a system, of an appliance. There's an appliance, in any WAN optimization case would have some x86 processor. Let's call it, let's say there's some Intel processor, it's an x86. This is the core engine in the system. So there's a NIC out here, so there's interfaces on this box, and number of interfaces, whatever they happen to be. A packet comes in, it's context switched to the control pin processor. So it goes up. Now the issue is that when a packet is received by this processor, the processor needs to do a bunch of things to that packet. Everything from a QoS decision, what do I prioritize it, how do I prioritize it, is it TCP or not? If it is TCP, what do I do with it? Do I do acceleration or not? What kind of acceleration? So it's a very iterative process. But the biggest hurdle, as we've talked about in other videos, is deduplication, right? In deduplication, there's everything from the fingerprinting to the SHA-1 hash to the hash lookup, etc., etc., etc. All of these things are happening in this one processor or core, whatever. They keep happening, right? Once all of these things are done, you send that packet out. Once all that work is done, then a new packet comes in. And then the same core will do the same work, and then the packet goes out again. It's very sequential, it's very iterative, but the bigger issue is, at a time, this core is doing one thing, rather processing one packet, but doing a lot of things, right? The fundamental issue with this is, how do you scale the system, right? So what a lot of companies have done is, what they do is, well, they buy, processors with more cores, right? So you can get 8-core big Intel processors out there, right? In our analysis, what we've seen is, if you do all the work that any one of the WAN-op companies is doing, per core, you maybe get 200 megabits. Best case, right? So, so one core, of course, depending on the company, if you don't agree with these numbers, I'm happy to talk to you, but this is our analysis. This is what we have identified our bottlenecks in a WAN optimization system architecture. So let's say a core can do, better color, a core can do 200 megabits or so. Sometimes it's less. Sometimes it's slightly more, but thereabouts. Let's say you get an 8-core processor. What's the best case scenario? 1.6. Interestingly enough, the biggest box in this market today, that's how fast it runs, about 1.5 gigs. We feel this is the reason why. Okay? So a lot of people argue, and it kind of sounds, intuitive in many cases that, oh, I'll just add more processors and I'll get done. I can add 10 of these and hey, I'll get 16 gig. Actually, it turns out it doesn't work that way. So every time you do things across sockets, so this is a single socket with 8 cores. If you have 2 sockets or 4 sockets, the overhead of sharing resources between sockets is so large that it itself becomes a bottleneck. So you really cannot build a system with multiple sockets, at least in an x86 architecture, given how memory buses work and so on. So if you do 2 sockets, it doesn't scale at all. Actually, in many cases, things get worse, especially if you're sharing dictionaries. End of the day, the issue is dictionary. I mean, it's either you're either memory bound or you're CPU bound, and then you become kind of memory bound. So we found that if you use multiple sockets, it doesn't scale at all, and we feel that this is why the WAN optimization guys can't really scale. In order to really scale up, well, they can do a few things. They can do less work, right? Which means you'll get less performance, right? Which is what happens in a lot of cases. You look at a lot of big vendors out there, as the speeds go up, the amount of work they do drops. In one vendor, what they talk about is they say, well, we do 32-byte matches for deduplication. If you're running at 2 megabits, yeah, maybe. If you're running at 500 megabits, not even close. They do maybe 1K, 2K, 4K matches. And the reason why is that, well, they just don't have enough time in the process to do all that work. So if you want to scale up, you have to give performance. And that's actually not a good choice, right? I mean, why as a customer, I don't want to make a choice that if I'm running faster, I should get less performance. Actually, that defeats the purpose of buying bound optimization or any such thing. So we really thought that this was not the right approach to this problem at all. More importantly, even if you solve this kind of cross-socket, maybe somebody tomorrow will have 32 cores per chip, right, per socket. Okay, so you get some number, right? But then how do I build a 20 gig, 40 gig box? It's not possible. You can't wait for Intel to build bigger and bigger chips forever. I mean, it's going to take Intel 5 years to build a big chip. What are you going to do, wait? No, so that's not the right approach for a customer. The approach we've taken is markedly different, and let me talk about that. So two things, if you read our kind of literature, if you talk to us, two words you'll hear over and over again. One is pipeline architecture, and the second is parallelism. Okay, those are kind of, those are words that we live by. Everything is pipelined at the software level, at the FPGA level, at the platform level, and everything, it's all about parallelism. So let me kind of give you a block level diagram of what our system kind of looks like. This is not the actual system, this is not the board, of course, some of that is IP, but I'll give you a sense for what it looks like at a higher level. So consider that this is the front of the box, so there's ports coming in and going out. Okay. What we've done is we've kind of broken down our system into 3 levels. There's a switch plane, there's a data plane, and there's a control plane. So the switch plane is making all decisions about what to do with the packets, and based on what the packets are, it sends them to the data plane or the control plane, or both, depending on what's going on. So there's a switch plane which kind of receives all packets, and it makes a decision about the packets. Now, a packet comes in. Let's say there's a packet that came in. Okay, it's decided that it should go to the data plane. So it will go to a data plane engine. Okay, that's a data plane engine 1. Once this packet moves to data plane engine 1, this switch plane is free to make decisions about many other packets. Okay, so by the time this guy gets packet 1, this guy is already working on packet 2, 3, 4, 5, 6, 7, whatever, because this is a much bigger engine, because it needs to make many decisions. So the first point to kind of internalize is that at one time, many things are going on, not just one packet. We don't wait for this one packet to kind of go through the system and then out and then we work on the second packet. That's just a wrong approach, right? You have to kind of do things in parallel. You have to make it in a pipeline. So people who've kind of studied computer architecture in college, they remember what a pipeline is, right? The idea is that you keep passing work and you keep taking on your work such that no single entity in the system is ever free. Everybody should be busy. That's the idea, right? So when this guy is done with 1, it sends it to, let's say, the dedupe engine. Let's say that's the example, right? Once this guy gets 1, this guy's already going to be working on 2 and maybe 3 at the same time. Who knows, right? It depends on what's going on in the system. And then this guy will send it to another dedupe engine for further analysis. And what this is working on 1, this is working on 2, this is working on 3, and so on. So the idea is that, and let's say this is some QoS performance thing that needs to happen for that packet. The idea is that there are many hardware complexes on the board. So if this were the board, the idea is that every one of these things, it's a hardware complex. Every one of these things is running at least 10 megabits. 10 gigabits. Okay? As long as each one of them is running at 10 gig, the bus connecting them is at least 10 gig, the entire system is going to be 10 gig. That's the architecture. It's a pipeline architecture. And as long as each one of them, and some of them obviously have to run much faster because the switch is making a lot of decisions, it needs to run much faster. So our switch plane, it's actually a 160 gigabit system. It's phenomenal. I mean, you will never ever need to use the entire system. You only have 4 10 gig ports on the front panel, which means worst case scenario, you can push 40 gig to a box. The switch plane will be fine. What it does actually is, if you actually send the box 40 gig, it will pick 10 gig that match a policy, it will accelerate that, and the rest of the 30 gig, they just kind of get switched out. We can do that because we have kind of designed this as steps in the system. Okay? So the switch fabric will take care of all that. It will only send 10 gig into the pipeline because this is a 10 gig pipeline. Okay? And each one of these guys is running at 10 gig, so the engine keeps moving. Okay? No engine is ever going to be slower than 10 gig. As long as each one of them is at least 10 gig, the entire system is 10 gig. okay? And if tomorrow, if we want to upgrade to say 20 gig, so as many of you know, we're working on larger systems, 20 gig, all we have to do is essentially build hardware complexes, which is a very simple thing to do for us, which can run at 20 gig. So we have to tune the systems to run at 20 gig. We don't have to change our algorithm at all. The architecture just scales up. The architecture scales up, the algorithm scales up, and the hardware complexes, we know from the market, these are kind of off-the-shelf silicon, they scale up too. We can easily do a 20 gig system depending on customer requirement. Today we are doing a 10 gig system because it looks like most customers are going to be, 10 gig is more than enough for many, but of course there's companies out there that want bigger ones for whom we are building a larger system already. And the fact that we can do a 20 gig system that quickly, even though the entire WAN optimization market took like 10 years to get to like 1.5 gigs. In 2 years we're going to go from 10 to 20, right? That's a testament to the fact that our platform is truly, it gives us a path to grow. It's a truly pipeline architecture. There's abundant amount of parallelism built in. Without this, you cannot hit the speeds that we're building today. 10 gig is not possible for WAN op. They can talk, the only thing they talk about is, well, you can have 10 of our boxes and you can load balance across them. These are not good ideas. This is just these aren't even band-aids. This is just embarrassing situations, right? When you don't want to be talking to a customer saying, hey, buy 30 of my boxes and I'll give you 10 gig. It's just, that's laughable, right? You want to do this with a single box, right, which we do today, and tomorrow we'll do 20 gig, and after that we'll do 40 gig. We can do this, others cannot.